Hello AP Physics students, this is Dr. Brenzi, and this is lesson A.1. This unit is going to be a very short unit on fluid dynamics, so it is a dynamics of fluids, how fluids move. You're going to learn that a fluid is simply a liquid or a gas. What we're going to be able to do in this lesson is we're going to be able to define pressure and density in fluids, and then calculate those quantities. And we're also going to learn about a law that shows the relationship between the pressure in a column of fluid as a function of depth. So those are the two things that we're going to do today. So let's go ahead and get started. First, a overview of what density is, and you may already be familiar with this, but I'm going to go over it anyway just to refresh your memory. So density is defined as the amount of mass per unit volume of a body. And that can be a fluid, that can be a solid. And we define that density, we give it a variable, a Greek letter, rho, and that value, density, is equal simply to mass divided by volume, and its units are measured in kilograms per meter cubed. Now, this letter rho, it looks a lot like the letter P, but when you write it, there's actually a curly stem at the bottom. So when you see me write my letter rho, I'm actually going to put a curl at the bottom. And this font, however, just doesn't show that curl, but other fonts actually show that there's a little curl at the bottom here. So make sure that there's no ambiguity between the letter rho and the letter P here, because we're going to use them both a lot. Anyway, enough of the letter rho. Another way that we can express density is to actually compare it to the density of water at 4 degrees Celsius, because that is the densest that water can get is actually at that particular temperature. And we call that comparison, that ratio, specific gravity. It's a unitless measurement because we're taking density divided by density, and so we just take the density of the object divided by the density of water. And if you're curious what the density of water at 4 degrees is, I actually forgot to look that up. I know it's somewhere around 1,000 kilograms per cubic meter. Let me see what the exact number is. Let's see here. Sorry, I should have had this ready already. Okay, so it is exactly 1,000 kilograms per cubic meter. So that density of water is 1,000 kilograms per cubic meter. Okay. All right, so that's density. And the other thing that we want to talk about in this lesson today is pressure. So a fluid, which is a liquid or a gas again, when it's at rest, it exerts a force perpendicular to any surface that it's in contact with. So so what we do in physics is we define a amount of force per unit area, because this force is going to be pushing on all of the areas of the container that it's in. And so what we can do is we can take a little piece of area, so we can zoom in to a little chunk of the wall and take an infinitesimal amount of area dA, and then the amount of force that the liquid exerts perpendicular to that area, you can take that divided by the area itself, and you will get the pressure. So in terms of a derivative, pressure is equal to dF dA, and that force is always perpendicular to the wall. I guess I'll say a little bit more about that, but I want to save that actually for our next unit, which is on temperature and stuff like that. So I'll talk a little bit more about pressure and why this is specifically perpendicular. But for now, let's just assume that that force is perpendicular to the wall. Pressure is exerted in every direction in a fluid, so it is a scalar value. It's not a vector like force is. In order to get the vector of the force it exerts, you have to know how the area is orientated. So pressure is a scalar, and the units that we measure pressure in are newtons per meter, but we give that a special name. We call it a Pascal. It's named after a guy whom you're going to learn about in lesson A.2. His name's Blaise Pascal, but we'll learn a little bit more about him and what he discovered about pressure. The other way that you can measure pressure is in terms of what's called atmospheres. Now, 1 atmosphere is the amount of air pressure that is exerted on everything around it at sea level. So air is a fluid, and at sea level, actually anywhere it is, it exerts pressure on everything around it, including you and I. And that amount of pressure is 101.3 kilopascals when we're at sea level. Now, up here in the Maha City, we're actually going to find out it's a little bit less than that. Okay, so those are the units of pressure that we use in physics. There are 2 different ways to actually measure pressure or report pressure. One is called gauge pressure, and the other one is called absolute pressure. Now, gauge pressure is the pressure that you would get if you stick a tire gauge inside your tire and measure how much pressure your tire has. If you had a flat tire like you see at the top there, then your gauge, when you put that gauge in the nozzle, is going to read 0. But that's not actually how much pressure is inside the tire. It just turns out that the amount of pressure inside the tire matches the amount of pressure outside the tire. So those 2 pressures are balanced, they're equal. So really the tire inside has an absolute pressure of 101.3 kilopascals, which is the same as the outside air. But your gauge would read 0 pascals. Now, if you fill up your tire with air, like shown in the bottom picture, and then you were to stick your pressure gauge on there, you might register a number that says, for example, 210 kilopascals. But that is the difference between the inside pressure and the outside pressure. If we wanted to get the absolute pressure, then we actually have to add on the pressure due to atmosphere outside, and we would get a number of 311.3 kilopascals. So gauge pressure is the amount of pressure inside the fluid minus the amount of pressure outside the fluid. In this case, the fluid is the air that you have inside your tire. Now, pressure, turns out, varies as a function of the amount of fluid that you have above you. So let's say that we have an element of fluid and it's at rest inside its well, let's say the element is at rest inside the fluid here. So this is the element of fluid that we're looking at right here, this black slab here, and it's at rest, and it has a bunch of fluid on top and a bunch of fluid on bottom, and that's what's in orange there. And what we can ask ourselves is, okay, if it's at rest, then that means that all the forces acting on that element have to equal 0. So what we're going to do is we're going to define a depth. And that depth is going to be the variable z, and it's going to have a value of 0 at the very top of the fluid, and then it increases as we go down. So the thickness of this element of fluid is dz. It's an infinitesimal thickness. And then it has an amount of mass, and we can actually calculate how much mass that has by taking the density of the fluid and multiplying it times the volume of this infinitesimal slab. And the volume of that slab just turns out to be A, the area, times dz. So the area A I'm referring to is this area on top or on bottom here. So that's the area A. That's A. Okay? Alright, now we know that since this is at rest, that there is going to be gravity acting on it. So there's gravity pulling it down, which is equal to its mass times g. In this case, its mass is dm, so we can write Fg equals g times dm. Now, if it were not at rest, or if this were the only force acting on it, then this fluid would just start free-falling. So there has to be some other force keeping this at rest. Well, it turns out that that force that's keeping this mass of fluid suspended inside the fluid is the difference in pressure between the top and the bottom. So the fluid on top of this element is exerting a pressure, or is exerting a force that equals pressure times that area A. And the stuff underneath, the fluid underneath the element, is exerting slightly more pressure. So we're going to call that P plus dP times A. So dP is just a little bit more pressure than what's being exerted on top. So the difference in these two pressures has to balance out this gravitational force. Since it's at rest, we know that net force is equal to 0. So let's write F net is equal to 0. So we're going to start off with this pressure on bottom, and that's pointing in the positive direction. And we're going to say, we're going to subtract off of that this pressure on top. So we're going to say it points in the negative direction. And then, of course, gravity is pointing downward, so we can say G times dm equals 0. Alright. It looks like if I take the difference between these two, that and that, I'm just going to get dP times A. Or I can rearrange it to say A times dP. There's nothing wrong with that. And then that is going to equal G times dm, so basically just added G times dm to both sides. And then I replace dm with rho times A times dz, and that's how I get this expression right here. Alright, well, it looks like I have A on both sides, so I can divide both sides by A, and then I get this differential equation. dP is equal to rho times G times dz. Well, if I want to integrate both sides from the top of the fluid all the way down to here, to the depth that this element's at, I can set up this definite integral. So I'm going to call P0 the pressure at the top of the fluid. There it is. And I'm going to call P the amount of pressure at this fluid element right here. So I'm integrating from P0 down to P, and that is going to equal rho times G, and then I'm going to integrate from 0 down to the depth Z that this element's at. And when I do that, I get this formula that gives the relationship between pressure and depth. P minus P0 is equal to rho times G times Z. And that's a very famous pressure versus depth equation. Sometimes you'll see it written as delta P equals rho times G times delta Z. That is acceptable as well. That just means you're integrating it at different limits. Instead of going from 0 to z, you're going from one z to another z. That's a little bit different, but basically the same result. All right. So let's actually look at, I believe I have an example coming up next. No, I don't. I have pressure gauges. Now, the way that we actually measure pressure, it works on this principle of how pressure varies versus depth. So one way to measure absolute pressure, actually the pressure of atmosphere, is to have a column of mercury. You have mercury inside a bowl, and air pressure is pushing down on it. So the amount of pressure down here is atmospheric pressure. And what you do in a barometer is you actually make a vacuum here so that there's no pressure there. So P0 is equal to 0. The P at the bottom is equal to atmospheric pressure. And then by measuring this height, how high this column goes, and then using our formula P atmosphere, or P P minus P0 equals rho GZ. Well, P minus P0 is just atmospheric pressure. So you can actually get the atmospheric pressure by knowing the density of mercury and knowing how high this column of mercury is. If you have ever listened to the evening news report and they're talking about the weather, sometimes they will actually report the pressure, the air pressure or the atmospheric pressure in terms of how many millimeters of mercury this column is. So that's actually what they're telling you. So they might say, oh, the barometric pressure is 29.6 inches and rising. Well, that means that this column of mercury is 29.6 inches tall, and it seems to be rising, so that means atmospheric pressure is getting greater. Another instrument that's commonly used to measure pressure is a manometer, and actually what it's devised to do, instead of measuring the atmospheric pressure, it actually measures the pressure inside a gas sample. And what you do is the pressure here has to equal that gas pressure, and then the pressure on top is caused by atmospheric pressure. So again, you're taking a difference between two pressures. So you get P gas minus P atmosphere is equal to rho times G times delta H. So you measure the difference in these two heights right here, and that will give you the amount of gauge pressure of this gas. Remember, gauge pressure is the absolute pressure minus atmospheric pressure. So those are two instruments, and they both take advantage of this fact that pressure varies as a function of height or of depth. Let's look at an example. Of how we could use this to calculate pressure. So let's say that we have a swimming pool, and it has a width of 9 meters and a length of 24 meters, and we fill it with water to a depth of 3 meters. So let's put those dimensions on here. And we're being asked to calculate the pressure on the bottom of the pool due to this column of water. Alright, so we're going to use our pressure versus depth equation. And I know that the density of water, I told you that earlier, we're going to assume it stays at 1,000 kilograms per cubic meter, even though this water is not at 4 degrees Celsius, but the density of water actually doesn't change all that much, really. So we can leave it at 1,000 kilograms per cubic meter. Alright, so we're going to, the amount of pressure at the bottom is P. The amount of pressure at top is atmospheric pressure. Don't forget we have a bunch of air pushing down on the top of the pool. So the top is going to be atmospheric pressure. And rho times G times Z I have there. Alright, what do I have next? Okay, So when I evaluate that, I get 29.4 kilopascals. And let's remember, since I'm taking the difference between the pressure at the bottom minus atmospheric pressure, I have actually calculated the gauge pressure. Now the problem didn't tell me whether or not I had to calculate absolute or gauge pressure. So in that particular case, as long as I specify whether I'm calculating gauge or absolute pressure, you should be able to get full credit for that. I shouldn't have to dock you points for that. But if we needed to calculate absolute pressures, we would just add the atmospheric pressure to it, and we would get 130.7 kilopascals as the absolute pressure. Okay, I hope that this was helpful, and it helps you through the lesson 8.1 problem set. It's going to be a short one, only 4 problems. When you finish those, bring those into me, and I'll give you some feedback on them. And I'll look forward to seeing you soon. Bye.